Ocean ecosystem health is on a decline, and we need insights to reverse the change. However, gaining these insights require a lot of manual efforts. In this project, I want to highlight my approach into alleviating some of this workload by introducing computer vision techniques. I'll be considering data acquired from the field trip of beautiful Vigo, Spain in relation to the so-called Living Ports project. Firstly, I want to give some general insights into our data acquisition methods and then touch upon building the actual computer vision model. The Living Ports project spans across 2 different sites in Vigo. First up, I want to highlight the efforts done in the harbor of Vigo, also known as Port Cultura. At the port, we find Nautilus, a floating observatory that allows you to get really close to the life in the harbor. As part of the D2 Aqua fieldwork here, our job was to lower cameras into the port waters and to measure the effects of biodiversity enhancing concrete elements created by ECOncrete. These concrete slabs are also referred to as seawalls and are designed with distinct patterns that are supposed to promote mussel and vegetation growth, which makes a better habitat for fish. As you can see in the video, we mounted GoPro cameras to these metal poles that were lowered a couple of meters below the surface. And these cameras recorded parallel to the seawall and are set to record 2-minute sequences every 30 minutes. Prior to going to Vigo, I was afraid that our footage wouldn't have any fish in it, but clearly this concern wasn't really justified. Next up, we're going to Busas. Busas is an artificial peninsula that is an extension to the port of Vigo. It reflects a piece of coastline that is more or less directly facing the Atlantic Ocean. At Busas, we find these so-called coastal locks that are designed to serve both as a means of coastal protection while also enhancing biodiversity. And a distinct feature of these coastal locks are that it holds a pool of water when the tide retracts, and this pool serves once again to promote vegetation growth as well as serve as shelter for various species like shrimp or fish in their early growth stage. At Busas, we went snorkeling and mounted GoPros on pre-installed screws at various depths. We did the same thing at a control site a couple of 100 meters from the coastal locks, where more traditional boulders were used as coastal protection. So these cameras were deployed for roughly 24 hours at a time, and sometimes we would have upwards of 20 cameras in the water at the same time. And while these were recording, I could get some work done in what is definitely the best office spot I've ever had. In the evenings, we would offload the SD cards and recharge the batteries. The field trip lasted a total of 3 weeks and was done by D2 Aqua on a half-yearly basis 3 times. As you can probably imagine, these field trips produce many hundreds and hundreds of hours of video data, and in the current setting, marine biologists are looking through all of this data manually in identifying and counting different species. And while the footage is arguably stunning to look at, it's also a lot of work to go through this manually. And this is where my proposed method of using computer vision comes into play. So the first step to this approach is to create a training dataset for a model to learn what a species look like and what is simply the environment. And this is done through quite an extensive labeling process where you draw boundary boxes around different species to tell the model what to look for. This dataset is then used to train computer vision models. And the first model that I'm proposing is a movement detection-based model combined with a convolutional neural network. So I use Gaussian mixture models as well as optical flow to detect movement in footage. And I use this to automatically draw boundary boxes around potential fish candidates. These boxes are then fed into a convolutional neural network. And in my case, I use something called ResNet 50. Which is then trained to identify if these boxes contain a fish species or if it's simply just the environment. Benefits of this model is that it's able to spot fish even though they're very camouflaged in the environment, but the model also suffers from being easily confused if there's a lot of movement from, for example, plants or very sharp light rays. The second model is called You Only Look Once, also referred to as just YOLO. It's a CNN-based model that works at a frame-by-frame level, meaning that the input is simply a single image. And like all CNN, YOLO uses kernels or filters that the models slide across an image to create an abstract representation of the image. And this is done for many filters and in many iterations, ultimately creating a low resolution but deep representation of an image, also known as a feature map. From this, the head of the YOLO algorithm is able to draw candidate boundary boxes and classify which species might be inside these boxes. This is done for all images in a video sequence, and voila, then you have analyzed footage. So, as you can see on this preview, the two models perform reasonably well in fulfilling this task, especially in these nicely lit environments from Boosas. There is still quite a bit of development to be done, and the models are far from perfect yet. Ideally, this technology still needs to be validated in different environments on different target species, but the results so far are at least pretty promising. One example of where the model really struggles in identifying fish is in this sequence, where you can see in the far background a lot of fish aren't being picked up by the model, in its current state at least. But as more data is acquired and labeled, it is the expectation that these models will only increase in performance. Overall, I think this technology has some really great promises, both within research but also commercially, which is why I also became a co-founder of Anemo Robotics, who aims to bring exactly this technology out into the real world to make a positive impact on biodiversity.